Hello, my name is Matthew Nealon, and in this video for homework assignment 5, we are going to be finding our equations for our adiabatic flame temperature. And once we find these equations, we're going to use these equations in a future video to then code out our temperature for our adiabatic flame. So we'll start off by drawing out our Bunsen burner, which is producing our flame. And since we have two inlets for our fuel, we're going to have natural gas, which is going to be just Ng. It's not going to be too important for this video. And then we have our air. And just for visualization, we'll have a little flame being up here. And since we've already found our chemical equations of the combustion reaction happening between natural gas and air, we're not going to worry about that. In this video, we are going to more worry about the calculations and the equations that are happening within this Bunsen burner here. So, what does it mean that this is adiabatic? So what does that mean? So with this, we can immediately assume we know that our change in enthalpy is going to be 0, and that means it's going to be steady state. And in our steady state, we can then assume a couple things, that our enthalpy going in minus our enthalpy going out is going to equal 0. Whatever's going in is going to equal what's going out. And a better way of writing it is just our total, and using a capital H to represent the total enthalpy. With this, we have our total enthalpy going in with our total enthalpy going out. And there's a couple assumptions we need to make here. Or not assumptions, but things we're going to ignore in this problem because we don't want to overcomplicate things. This is not, we're using an ideal gas for this problem. So we're going to be ignoring a couple things to get misspelled out a little bit. We're going to be ignoring a couple things to further simplify our equation that we're going to use in our coding section, or what we're going to find. We are going to ignore the heat loss that our flame is going to produce, or the heat loss of our flame as it's traveling up our Bunsen burner or to the sides. So we're going to ignore heat loss from sides. We're also going to ignore our non-flow work. And we're also going to ignore the kinetic energy in which our gas is going to produce. With all these, we can then start to derive our equations. So with sort of this, with this equation up here, we can then use this as a sort of starting base in where we can start finding our quote-unquote change in enthalpy, or derive how it is going to work with us. So we can then say that our change in enthalpy is equal to our change in temperature multiplied by the heat capacity. However, we want to state this in different terms than it is right now. We want to state this side of the equation. We want to state our right side of the equation a little differently. So it's going to be our change in temperature times our change in enthalpy multiple, and under that is going to be our change in temperature, or a derivative in terms of temperature, and it's going to have a constant pressure. What this says is that our change in enthalpy will then be in terms of our temperature, or change in temperature, and our pressure is going to be constant. Or another way of writing this is that delta H, or another change, is going to be equal to our heat capacity. Sorry, I meant to say our heat capacity equation can be used in this as such, and then it's going to be our change in temperature. This is what we want for our change in enthalpy equation. However, there's a couple things we need to state as we start to derive our equations. With this, we need to at least clarify a couple details. Since our enthalpy is dependent on our temperature, this equation here is only able to be used in very small ranges of T, or temperature. It can't be used over very large periods of time, or temperature ranges, because that heat capacity will change depending on what the temperature of the actual of the material is, or the temperature being produced. Sorry, our heat capacity will change, so we need to clarify this. So this is only for small changes of temperature. Sorry, that's a little cramped there. However, there's another equation we can use that will then represent even larger ranges, that can represent the larger changes of enthalpy change. So we're just going to separate that off, and we're going to start with our delta H. Then going to be equal to, it's going to be an integral, and our change in enthalpy is going to be equal to the integral of our enthalpy changing from our first enthalpy to our second enthalpy, and then that would be equal to our equation here in other terms. So it's going to be our temperature, or sorry, I messed that up a little bit. It's going to be our temperature values and our heat capacity in terms of our temperature. And this represents our larger changes in enthalpy. And this represents the bigger changes. So it's going to be, so we'll just write this out as so. This equation represents our bigger, because with heat capacity, our heat capacity will change as we sort of grow in temperature. So we need to represent that with the second equation here. And the last thing we want to do before we start coding with this is that we were told to find an equation of heat capacity on ChemCAD. However, I found the equation we want to use on ChemCAD, and before I started recording this video, and it is as such. And with this equation, we are then going to integrate its various parts to then use later on in our coding section to represent these changes of heat capacity as our temperature changes. So our heat capacity equation that we found with ChemCAD is going to be equal to as such. It's going to be our A parameter plus our B parameter, and that B parameter is going to be multiplied by a C parameter that is being divided by T, and that whole first equation, or that our C parameter divided by T is then going to be on top of another fraction, which is going to be our hyperbolic sine function, and then it's going to be, and within the parentheses of our hyperbolic sine, it's going to be the same thing on top. So it's going to be our C parameter divided by temperature. And that whole thing is then squared. And then our next thing we want to do is our second part of our our heat capacity equation. So we have a D parameter similar to our B parameter. It's getting multiplied to this side. It's getting multiplied to this squared equation. So D is being multiplied to an E parameter divided by temperature, and then it's going to be a hyperbolic cosine and then within those parentheses it's going to be the same thing on top again, just like our first hyperbolic is going to be E divided by temperature again, and that whole equation is going to be squared. However, we need to take the integral of these squared values here, because this is going to determine, because we can take the integral for the rest of this parts, but these two parts of these equation here is going to be really difficult to integrate. However, with ChemCAD, we also can use integrating software like Wolfram Alpha, which is an integrating software we can use, and from this we can then integrate as such. So our integration for this part of the function, so I'm going to write it out. Sorry if you hear church bells in the background. So this whole function is then going to be equal to, or this will be integrated to, sorry, forgot to put our functions being integrated with respect to. So this whole function is then going to be integrated into this function. So it's going to be our C parameter on top of this fraction, and it's going to be our tangent, our hyperbolic tangent, and then we're going to have our C parameter divided by our temperature, and this is going to be our integrand for this function here, and now we can then integrate for our hyperbolic cosine. And this is going to be a slight difference since we're not dealing with a hyperbolic sine anymore. We're dealing with a hyperbolic cosine. So we're just going to write this out real quick. And then this will then be used to represent our, and then our integrand here will then be integrated into our E parameter multiplied by a hyperbolic tangent, and within that hyperbolic tangent it will be E divided by our temperature value again. And these are all our equations we need to use that represent the relationship in which our adiabatic flame is going to be calculated. And then we can start plugging all of these equations in later on with Python and various NumPy programs and optimizers to then find our temperature for our adiabatic flame.